Okay, so welcome to Math 310, Lecture 6. I'm just trying to see, okay, good, it is recording. And so what we're going to do today is we're going to continue with the introduction to groups, doing more properties, doing more examples. So just to remind where we were last time, we were talking about the order of a group. Okay, the order of a group, the number of elements. And if we have an element G, the order of the element G is what is the smallest positive integer that we need to use to get back to the identity. So if I cube something and it's the identity, what other power will return me to the identity? So if G cubed is the identity, what's another power of G that would be the identity? Not anything. So if G has order 3, 3 is the smallest positive integer that's going to return G to the identity. So G is not the identity, G squared is not the identity, but G cubed is the identity. G to the ninth. Is there anything smaller than G to the ninth that would work? G to the ninth would work. G cubed works. How did you get from G cubed to G to the ninth? Yes. G to the sixth, right? G to the sixth works. G to the ninth works. What else works? Should be able to give me infinitely many examples now. G cubed works. G to the sixth works. G to the ninth works. G to the 12th. G to the 15th, right? Every time I have a G cubed, that's just the identity. So there's going to be infinitely many choices of n that will work. And so it's very important that when we talk about the order, we're talking about the smallest positive integer that works. Once there's a positive integer that works, there's infinitely many. And the smallest one that works is going to be the order. And so the theorem is that if I give you a group G and it has finitely many elements, then the order of G, little g, is going to divide the order of the group. And so we talked a little bit about how might you try to prove this? Well, if G is the identity element E, what power of E do I need to get back to E? What's the smallest positive integer that will work? 1. It's already the identity. So if I take little g to be E, n equals 1, and 1 divides everything. So yeah, this is not a big deal to prove. So now let's assume we have some element G that's not the identity. And we can start looking at powers of G. We have E, then G squared, then G cubed. And because we have a finite group, we can't have infinitely many distinct things here. If there's only 50 elements in the group, once I list 51 elements, I know there has to be a repeat. This is the pigeonhole principle. So at least 2 of them have to be the same. I can't keep getting infinitely many different things. So we know 2 of them would have to be the same. Say G to the K equals G to the L. So if you want a specific number, say G to the 4th equals G to the 11th, we can multiply both sides by G to the minus 4. That's 4 inverses of G, and then we would get E equals G to the 7th. So once we know that an element repeats, when we look at this list of powers, we know that some power of G is going to be the identity. Maybe we just got E, G, G squared, G, G squared, G, G squared, and we never got back to E. We just cycled. That's not going to happen here. And so every element will have a finite order. And so eventually, maybe it was G to the 7th is going to be E, and then it's going to just keep repeating. G to the 8th is going to be the same as G times G to the 7th. G to the 7th is E, so we just get back G. So we want to show that this is going to, whatever the order is here, it's going to divide the size of the big group G. And so if we say that the order of little g is n, we could look at the set E, G, G squared, all the way up to G to the n minus 1. These will be all the distinct powers of G. And when we get to the next one, G to the n, that's going to just be back to E, because G to the n is E. And then G to the n plus 1 would be just g. G to the n plus 2 would just be g squared. What does this kind of look like? Where have we seen this before? Modular arithmetic. We're just going to keep cycling around. So we then notice that this set, g squared, actually is a group. And we can go through and we can show that it's closed, that it has an identity, that it has an inverses, that it has the associative property. Some of these are easier to prove than others. Your associativity, everything in here lives inside the big group G. Since the big group G was associative, this was associative. The big group G is closed, but we don't necessarily know that when we multiply two things like this, it's going to stay in the smaller set. We know it has to live in big G, but maybe it doesn't live in this cyclic group g squared up to gn minus 1. So you have to do a little bit of work to show that it is closed. The identity, well, we've got it right there. We know that there are inverses. You just have to show that the inverse exists. So a really good exercise is for you to put in all the details of this. You should be able to write this up cleanly. I'm happy to take a look at an attempted write-up, okay? But I strongly urge you to try to write up a rigorous proof that this is going to be a group, okay? So we're going to prove the proposition now, but something stronger is true than the proposition. What the proposition is saying is, I give you a group capital G, the order of any element little g divides the size of big G. A stronger statement is true. If I give you any group G, and I look at any subgroup in that group, then the size of the subgroup divides the size of the entire group. So one way to prove proposition 2.13 is don't prove it for the specific subgroup generated by little g. Prove it for any subgroup, and then say, and now I choose this to be my subgroup. So this is one way we can do things in mathematics. We can prove something at a very high level and then specialize. The other thing we can do is we can exploit what's going on for a specific problem. So instead of trying to prove something in great generality, maybe I can use some additional nice features of this. Okay, so this was proposition 2.13, yes. Okay, so proof of proposition 2.13. So we have G is a finite group. G in G has order n, and I'll assume that n is greater than 1. If n equals 1, what element does G have to be? What's the only element that has order 1? E. E. And the result is clear when it's E. So I'm going to just assume n is greater than 1 if I want. Okay. So we need something to represent the size of the group. Let's let capital N equal the size of G, the number of elements of big G. To me, this seems like reasonable notation. I'm using little g for group element and little n for its order. I'm using capital G for the group. Let's use capital N for its order, for its size. Is it possible that little g could have an order larger than big N? So I have a group. We're looking at the set g squared dot 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 g n minus 1. And this is contained in G. And little n is the smallest power such that I return to E. What would happen if little n was greater than capital N? So capital N is the number of elements of big G. What would happen if little n was larger than big N? Why would it not be in G?
All the elements Little g has to be in big G for it to be contained in the set.
Okay. And so how do I get a problem if little n is bigger than big N? If little n is larger than big N, then what's the issue? Why isn't little g in it? I mean, I'm assuming little g is some element in big G. What's the contradiction? What would go wrong if little n is bigger than capital N? How many elements are on the left-hand side here? Nope. N, right? Because I start off with E. Think of this as G to the 0. I have little n elements on the left. How many elements are on the right? How many elements are in big G? Capital N. So could I have, say, 23 elements in a group of size 15? The left-hand side is contained in the right-hand side. Can the left-hand side have more elements than the right-hand side? No. So I have to have little n less than or equal to big N. If little n is greater than big N, then more elements in E, G, G squared, dot, 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 G n minus 1 than are in G. That's absurd. So little n has to be less than or equal to big N. It's possible that it could equal big N. Maybe G is just, this big G is just E, G, G squared, G cubed, all the way up to G to the N minus 1. That's possible, but I know little n can't be larger than big N. So we can write big N as some multiple of little n plus a remainder. So they mentioned this in chapter 1. You've all seen this before, right? If I want to divide an integer by another integer, I can write n as a multiple of my integer, and then there's going to be a remainder. What can you tell me about the remainder? And what's true about the remainder R?
It's integer and always positive, or it's between 0 and n.
Good. And 0 less than or equal to R, you're almost right. You are correct. You are correct that it's between 0 and n, but you can do a little bit better. You are off by the smallest amount possible from the best statement. Could it be 0? Sure. Could it be n? What if R equaled n? What could we then do? Right? Because we could then increase little a by 1. So R is strictly less than n. If I'm dividing 15 by 5, I don't say it's 2 with a remainder of 5. I would say it's 3. So when we divide, what's nice about this is the number you get back is going to be smaller than the number you started with. I'm dividing it by little n, and my remainder is going to be smaller. Okay. How can this be helpful?
We need to prove that R equals to 0 or the.
So if we prove R equals 0, then we're done, right? Great. So we want to show R equals 0. Because if we can show R equals 0, then we've shown n is a multiple of, big N is a multiple of little n. Okay, so how could we show that this is the case? So what could we try to look at? What are the only elements we know? So what elements do we know?
G and then E.
So we know G and E. And what numbers?
Big ends.
Big N, small n. And we now know two other numbers.
R.
R and A. So again, abstract algebra, modern algebra, this is a hard class. Let's write down what we know and try to figure out how can we use this. So the only elements we know are E and G, maybe G inverse as well, but that's it. We just know E and G. And the only numbers we know are N, big N, little n, R, and A. So it seems like we want to raise G to a power. What would be a good power to raise G to?
N,
N. Which N?
little n.
Little n. Okay. G to the little n equals E, that's known. So we're not going to get anything new from that. Anything else we could try to raise G to? What else could we try? I'm sorry?
The other end.
The other n. And what do you think G to the big N is?
G to the N plus R.
So we know G to the big N is G to the AN plus R. This is going to be G to the AN times G to the R. This is, I'm sorry, it's a small n. And it's going to be G to the N to the A, G to the R. But what is G to the N? What's E to the A? E. So this is just going to be G to the R. So we know if we raise G to the nth power, capital Nth power, we get back G to the R. Okay. What element do you think G raised to the nth power should be?
The big N.
Yeah, what do you think it should be? So we know G to the little n equals E. We know G to the big N is G to the R, where big N is A little n plus R, 0 less than equal to R less than n. If I take an element in a group and I raise it to the size of the group, what do you think I'm going to get?
G,
So you think I would get back to where I started? So best thing we could do is get some data. So let's look at a clock group under multiplication. Let's look at the stuff 1, 2, 3, 4 under multiplication mod 5. So we're gonna make a little table. So 1, 2, 3, 4, 1, 2, 3, 4. Some of these are easy to fill out. What happens when you multiply anything by 1?
Yes.
You get some. 1, 2, 3, 4, 1, 2, 3, 4. What's 2 times 2 mod 5? 4. What's 3 times 3 mod 5? 4. What's 4 times 4 mod 5? Nope. 1. What's 2 times 3 mod 5? 1. What's 3 times 2? Also 1. What's 2 times 4? Mod 5. 8, which is 3. So 4 times 2 is 3. And then left with 3 times 4 mod 5 is 2. So here's the multiplication table. Okay. So the first thing is, have we now shown that this is a group? Well, we can see that it's closed, that whenever I multiply something mod 5, I'm going to have something mod 5. I'm not going to get a 0. Okay, good. Does every element have an inverse? Is there an inverse to 1? What would be the inverse of 1? 1. What would be the inverse of 2? What times 2 equals 1? 3. Is there an inverse of 3? Yeah, it's going to be 2. Is there an inverse of 4? Yeah, it's its own inverse. So we've got a closure, we have inverses. Do we have an identity? Yes, we have the identity 1. The last thing to do is to check associativity, but because regular multiplication is associative, this will be associative. This is a group. What happens if we take, how many elements are in this group? 4. What's 1 to the 4th power? 1. What's 2 to the 4th power? 1. 2 times 2 is 4. 4 times 2 is 3. 3 times 2 is 1. So 2 to the 4th is 1. Another way you could have done it is 2 squared is 4. So 2 to the 4th is 2 squared times 2 squared. Okay, what about 3 to the 4th?
1.
It's also 1. And you can do the algebra, or you could note that 3 to the 4th is the same as 4 minus 1 to the 4th, which is congruent to negative 1 to the 4th, which is just going to be 1 mod 5. And the last one is, what is 4 to the 4th? That's also 1. So notice in this example, when I take any element and I raise it to the size of the group, what do I get?
Identity.
I get the identity element. What might you conjecture G to the capital N should be? Is this enough data to make you happy and worth and reasonable to conjecture? All right, good. So we've at least known each other long enough that you're now hesitant to conjecture based on one data point. Right? You need at least 2. 3, how many?
I'd like a proof.
You'd like a proof. Okay, so let's hold off on this for now. And let's talk a little bit about some examples of groups, then we'll return to it. Okay, so chapter 2 has lots of examples of groups. So you should be going through, you should have read all of chapter 2 by now, and you should have gone through lots of different examples. So there's the group of integers and the integers modulo m, and these are under addition. We could also talk about, real rational complex numbers under addition. There's no problem. Multiplicative group is a little bit more interesting. What number do you have to make sure you avoid if you're doing the multiplicative group?
No.
0. Every other number will have a multiplicative inverse. There are cyclic groups, and that's basically what we've been looking at when we've been looking at the group generated by one element. E, G, G squared, dot, 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 G to the n minus 1, and G to the n equals the identity no smaller n words. So these are cyclic groups. These are really nice. Each element is just a multiple, the same multiple from the previous. You've seen this maybe with geometric series, 1 r squared r cubed. The difference now is some power is going to return to the identity. So if you want an example, so example for 2.18. What's the square root of -1? We call that I. So if I look at what's generated by I, that would be 1i. I squared is -1. Then you would have -I. And that would be an example. If you're familiar with complex numbers, I could do, let's say G is equal to E to the 2 pi I over N. And then the group generated by that would be 1 e to the 2 pi I over N, e to the 2 pi I 2 over N, e to the 2 pi I 3 over N, dot, 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 e to the 2 pi I n minus 1 over N. And these would be nice examples of cyclic groups. And then I'll let you look in the book for the permutation groups, the matrix groups, the dihedral groups, the quaternion groups. These are a generalization of complex numbers. Has everybody here seen the complex numbers before, x plus iy? How many of you have seen the quaternions? Okay, what's the biggest difference between the quaternions and the complex? Do you remember?
Complex is 2 numbers, quaternions is 3.
Nope.
4.
4. Quaternions are 4 numbers. Do you know a difference between the complex numbers and the quaternions? So, are complex numbers nice? Is it hard to multiply 2 complex numbers?
Harder than regular.
Harder than regular ones. Does order matter? Is Z1 times Z2 the same as Z2 times Z1? Yeah. For quaternions, you lose commutativity. So we have the reals, which is 1 dimension, the complex, which is 2 dimensions, the quaternions, which is 4 dimensions. What do you think comes next? It's almost perfectly timed. A 1-dimensional thing, a 2-dimensional thing, a 4-dimensional thing. What do you think might be next?
8.
8, the octonions, and you lose associativity. Yeah, it gets worse and worse and worse in terms of how you try to push these forward. But you can come up with some really interesting structures. Okay. What I want to do now is talk about clock arithmetic under multiplication. Okay, so let's start off with a good number of hours for clock to have. Anybody want to give me a good number of hours for clock to have? Imagine you're talking to a 6-year-old cousin of yours. How many hours should we do?
12.
12. All right. So let's do a clock with 12 hours under multiplication. So we have to make a multiplication table, right? Oi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Those are the numbers that are going to be relatively prime. I don't include 0, right? And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is a lot of stuff to fill in. In the 21st century, should I be doing this by hand? No, I write a computer program to do this. All right. Is it easy to figure out what happens when I multiply by 1? Yeah. All right. This row is not going to be much of a challenge. So this is going to just be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 1, 2, going down 3, 4, 5, 6, 7, 8, 9, 10, 11. So what's 2 times 2 on a clock with 12 hours? 4. What's 2 times 3? 6. What's 2 times 4? 2 times 5. 2 times 6. I can stop. Right? I don't need to fill out the rest of the table. This is why I was willing to do it. I knew I wouldn't have to get far before. Is this going to be a group? No. Why not? It's not closed. Well, you know what? It's the 21st century. Let's be a little bit more accommodating and accepting. It's okay if it's not closed. I'm not going to let that bother me. Let's keep multiplying. What's 2 times 7? 14. And what's 14 on a clock? 2. 2 times 8? 4. She knows we just keep increasing by 2. 2 times 9? 6. 2 times 10? And 2 times 11? So even if I was willing to accept the fact that it's not closed, what's my next problem? I'm sorry?
I don't know.
So it's not closed. So that's one property that fails. Is there another property that fails? Do we have an identity element? Yes, not closed, so that's bad. Has an identity. That's good. Associativity, it's going to inherit that, yes. What's the last property to check? Inverse. So some elements have no inverse. So even if you are willing to be a little bit understanding and say it's not closed, which you can't do that. But even if you were, it still has serious problems. So the solution is to be undemocratic. Okay, this is one of the only times when you can advocate for something like this. What should we do to an element like 2? We're looking at our numbers under multiplication. 2 is causing trouble. What should we do with it? We move it. We're not going to try to reform 2. We're not going to try to make 2 behave. We're just going to exclude it. You're gone. You're no longer going to be considered. Okay? We can do that here. We can't do that in other places. But 2 is causing us trouble, so goodbye. So any thoughts about if we're going to get rid of 2, what else should we get rid of? As soon as we're getting rid of 2, what else do we have to get rid of? We have to get rid of 4. And what else? 6, 8, and 10. Those are all gone. I'm not going to look at those. What about 3? Let's try working with 3. What's 3? 3 times 1 we know. What's 3 times 2?
6.
Yeah, but I don't care.
Yeah.
Because we've gotten rid of all those numbers. So I don't care that 3 times 2, I do care. But this problem, I don't care that 3 times 2 is 6. What's 3 times 3? 9. 3 times 4, I don't care about. 3 times 5? 15, which is the same as 3. 3 times 7? I'm sorry? It's not 1. It's 9. 3 times 9. That's 27. 24 is the same as 0, so it's going to be the same as 3. 3 times 11, 33. So 24 to 33 is 6, 7, 8, 9. What do you think about 3? It has no inverse. The multiplication is still going to be closed, but it has no inverse. What should we do with 3? Remove it. You're gone. And if we get rid of 3, what else do we have to get rid of? 9. Oops. So 3 is gone, 9 is gone. We're left with now 1, 5, 7, and 11. So things are now much smaller. I'm going to just redraw that down here. 1, 5, 7, 11, 1, 5, 7, 11. Okay. What's 1 times 1? Well, okay, we can do those. 1, 5, 7, 11, 1, 5, 7, 11. All right, 5 times 5 is 25, which is the same as 1. Thank you for not using a specific finger. 5 times 7, 35. 36 is the same as a multiple of 12. So sometimes it's better to overshoot and fall back. So if it's 1 less than a multiple of 12, it has to be 11. And then 5 times 11 is 55. 48 is a multiple of 11, so this would be the same as 7. 7 times 7, 49. And 49 is 1 more than 48. 7 times 11 is 77. 12 times 5 is 60. 72, so this is going to be 5. And last, 11 times 11 is 121, which is 1 more. All right, do we have an identity element? Yes. Are things associative? Yeah, that's easy. Is it closed? Is everything either a 1, 5, 7, or 11? Yes. Does everything have an inverse? Yeah, the inverse of 1 is 1. What's the inverse of 5? Itself. What's the inverse of 7? Itself. And the inverse of 11? Also itself. We have a group. We have a group with 4 elements. Each element is its own inverse. If I give you the equation x squared equals 1, how many solutions does x squared equal 1 have if you're in high school?
1.
X squared equals 1.
High school?
In high school. You should have 2 solutions to x squared equals 1.
-1.
1 and -1.
You do that in high
Yeah.
school?
Yeah. X squared equals 1. If you go down to elementary school, it might just be 1.
Well, there.
Yeah. If you go down to elementary school, it's just 1. If you go down sufficiently far, it could be like 13. Here, if you look at the equation, I want to solve x squared equals e. X squared equals e has 4 solutions. One of the best quotes I remember from any of my books in high school was our physics book, and it talked about special relativity, and it said, yeah, these results may seem counterintuitive, but most people don't have experience traveling at 3/4 the speed of light. I liked the most people. I don't know anybody who has any experience traveling at 3/4 the speed of light. So one of the worst things you can do is you can take data from one area and apply and say it holds in another. It's not bad to maybe have that as my baseline. If you've done some statistics, maybe my prior, but then get some data and see, is this reasonable? If I give you the equation x squared equals 1, I would expect there to be, 2 solutions. We now have a situation where x squared equals e, the identity element, has 4 solutions. Every element of the group satisfies this. So now, can you tell me anything special about the numbers 1, 5, 7, and 11 on a clock with 12 hours? Why did these numbers survive? They're relatively prime. So do you think if I only look at the numbers that are relatively prime, I will have a group under multiplication? Is one data point enough? No. But it seems maybe reasonable. So this leads to trying to understand clock groups under multiplication. So the first lemma, if n is composite, 1, 2, dot, 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 n minus 1 is not a group under clock multiplication. Okay, we always have to exclude 0. 0 can't be in the set. So if n is composite, I claim that this can't be a group. So let's try to prove this. There's lots of ways to prove it. All we have to do is find one property of the group that fails. To be a group, you have to have an identity, you have to be associative, you have to have inverses, and you have to be what else? You have to have identity, inverses, associative, and what's the last property to be a group? Closed. It's going to be associative. It's going to have identities. So we're down to either something doesn't have an inverse, or there are two elements, and when you multiply them, it's not in the set 1 through n minus 1 on the clock. Which do you think we should try to do? Prove something doesn't have an inverse, or prove that it's not closed? Not closed. That's what I would do. Both of them can be done. So we're going to show it's not closed. We'll show it's not closed. Since n is composite, what do we know? What does it mean for a number to be composite?
Non-prime.
Non-prime. So what does it mean to be non-prime? Okay, so we can write n as, say, maybe n1 and n2, where each is greater than or equal to 2. Right? Can you give me two numbers that multiply to something that's not in the set 1 to n minus 1 on the clock? So can you give me two numbers between 1 and n minus 1 that multiply to something that's not between 1 and n minus 1 on the clock? For example, if n equals 12, then I could write n equals 3 times 4, or n equals 2 times 6. So can you give me two numbers that if I multiply them, each number is between 1 and n minus 1, but when I multiply mod 12, I don't get something between 1 and n minus 1. Give me two numbers that would work on the clock with 12 hours. 3 and 4? Where'd you get 3 and 4?
Because it's always n minus 1, so it's, oh, okay, yeah.
It's the factorization of n. Give me another number, another pair of numbers that won't work. 2 and 6 from another factorization of n as a product of two numbers that are at least 2. So in general, if n equals n1 times n2, each nk greater than or equal to 2, then n1 times n2 is not an element of our set. under clock multiplication. So it is not closed. And this is one way to prove it using the givens. What am I told? I'm told n is composite. So this was one proof. Let's do a second proof. Oops. Proof number 2. So which property we're going to try to show now fails?
Can you read the line above again?
In general, is that the line? So in general, if n equals n1 times n2, each nk is greater than or equal to 2, then n1 times n2 is not in the set 1, 2, ... n minus 1. Because n1 times n2 equals n. So the givens helped us figure out how to find our counterexample. We're trying to show that it's not closed. So to show that it's not closed, I just have to find 2 elements such that when I multiply them, I get something that's not in the group. How can I find those 2 elements? Well, what do I know about n? I know it's composite. What does it mean to be composite? It means I can write it as n1 times n2. And that's going to help influence how I do things. The next one is to try to show a number is not invertible. What number do you think we might be able to show is not invertible?
0.
Well, 0 is not going to be in our set. So we've already removed 0. But which other elements, when we looked at what was going on before, which numbers, what was the first number that we showed was not invertible? It was 2. And what's the relation between 2 and 12? They have a common factor. So when we're trying to do things in general, what number do you think might be possible to show doesn't have an inverse?
And then n1.
N1 and N2, right? So if n equals n1 times n2, each nk greater than or equal to 2 will show, n1 is not invertible. Okay. Imagine it was. Imagine n1 has an inverse on the clock with n hours. What does it mean for n1 to be invertible?
There is just a number and one inverse.
Okay, so there exists a number, I'll call it A, such that A times n1 equals what?
N1.
What's it supposed to be equivalent to on a clock if it's invertible? If you're the inverse, what happens when you multiply by the inverse? What are you supposed to equal? The identity. So it's supposed to be equal to 1 on the clock. So it's congruent to 1 mod n. That means there exists a B such that A times n1 equals 1 plus some multiple B of n, or A times n1 is 1 plus B n1 n2. Is everybody comfortable with how we got here? If it's invertible, I can find some number A such that A times n1 on the clock gets me to 1. It doesn't mean it has to actually equal 1. It's equal to 1 up to some multiple of n, up to some multiple of the number of hours. And so now I'm just unwinding, what does that mean? What does it mean for them to be equal to each other on the clock? It means the sum number of B such that they differ by B multiples of n. And n is n1, n2. So if you look at this, what can I do? I've got a n1 on the left. I've got 1 plus b n1, n2 on the right. How do I get a contradiction from this? So I've got to get a contradiction. I've got to show there's no choice of A or B that will work. No matter what A and B you try, this can never happen. So you've got to look at the two sides of the equation. On one side, you have A and 1. On the other side, you have 1 plus B and 1 and 2. What could you try to do? We've got to get a contradiction somehow. Do you want to move things around at all? Do you want to collect any terms together? Any thoughts about what we could try to combine? So in the old,
Wouldn't be 1 mod and 1.
it wouldn't be correct. So how could we group that? How would we do the algebra?
So it would be 1 plus bracket b n2 n1. So it would mean that n1, a times n1 would have a remainder of n1, which cannot happen, I guess.
You're close, but let's think back to solving algebra equations. So I give you 3x equals 7 plus 4x. What would you do? How would you solve this? You bring all the x's to one side, right? I've got an n1 on the left, I've got an n1 on the right. Let's put them together. So thus, a n1 plus b n1 n2 equals, I'm sorry, that's a minus. Right? And now, how can I rewrite the left-hand side? How can I rewrite a n1 minus b n1 n2? What do you notice happens in all those terms?
All the terms on the left have it.
They all have an n1, so let's pull out an n1. So this is a minus b n2 times n1 equals 1. So n1 divides 1. That's impossible, as n1 is greater than or equal to 2. And so this would be another way to prove our result. So again, I'm trying to use the fact that I know that it's composite. So because it's composite, I can write it as n1 and n2. I'm trying to find some element that's not invertible. It's what do I have in play? I don't have much. Now, I'm not saying that there's only one way to write n as a product of two numbers that are at least 2. If I give you a number like 12, I can write 12 as 3 times 4 or 2 times 6. I'm not going to really jump for joy and say 4 times 3 is a possibility. Come on. 4 times 3 is the same as 3 times 4. But 3 times 4 and 2 times 6 are two very different ways. And this will tell me that the numbers 3, 4, 2, 6, they're not going to be invertible. And so, again, I'm trying to go through as many times as possible the mindset of how do you attack problems like this. If I'm going too slow, let me know. If I'm going too fast, let me know. Shoot me an email after class. What I'm probably going to do is I'm going to give a test on Thursday. You are not allowed to write your name on it. Okay? This will be a chance to get a sense of how you're doing. Okay? It'll be open book. Don't make yourself crazy in studying, but this will get you, some data set, some data point as to how are you doing with the proofs like this. Okay? And so I want to get a really good assessment early on. I do not want it to be a stress-inducing thing, okay? And so even if I say I'm not going to count the exam, I know people are going to be a little bit worried if their name is on it, okay? So all I ask is that you write something that should uniquely specify you. Yeah, have at least your 14 characters. Okay. Yeah, I will just hope that nobody chooses the same long string as someone else. Okay. But hopefully, as we keep doing problems like this, we just show that if n is composite, this is never going to be a clock group under multiplication. One possibility is we might be able to fix things by saying, rather than looking at all elements, let's just look at the elements that are relatively prime to the number of hours. In the case of 12, that worked. That did give us a group. Maybe that always works, or maybe something was special with 12. So one way to try to fix things is to say, from this point onward, let's only look at the elements that are relatively prime to the number of hours. Another possibility is maybe we don't look at composites. So if we don't look at composites, what does that leave us with? Almost. Primes and what else? And the number 1. 1 is not considered prime. Does anybody know why 1 is not considered a prime number? I'm sorry? So why do we say a number is prime if it has exactly 2 factors, itself and 1? This excludes 1 from being a prime. 1 is not a prime, it's not a composite, it's called a unit. Have you seen the fundamental theorem of calculus? Okay, you don't get fundamental lightly. Okay, it's major to be called fundamental. There's the fundamental theorem of arithmetic. Any integer can be written uniquely as a product of primes in increasing order. So can somebody write 12 as a product of primes in increasing order? Really hope so. Come on, 12. 2 times 2 times 3. Right? I could also write it as 2 times 3 times 2, but that's why I say in increasing order to have a natural canonical representation. If 1 was considered a prime, how could you write 12? How else could you write 12 as a product of primes in increasing order if 1 were a prime?
2 times 3 times
1. Okay, we want increasing order, so
1 times 2.
1 times 2 times 2 times 3. I was actually thinking of 1 to the 1701 power times 2 times 2 times 3. Or 1 to the 24601 power times 2 times 2 times 3. You lose unique factorization if 1 is considered a prime. So it's convenient 1 is not a prime. So if I want to look at other choices of n, I could take n to be 1, which would be very boring because then the only element is 1. It's going to be closed because 1 times 1 is 1. 1 is its own inverse, it's associative. It's boring, but that's a clock. And then I'm left with primes. So what if n is prime? So what if have a clock with p prime hours under clock multiplication? Do we think that this is going to be a group? So we could try a specific example. We did 5 before. We could try 7 and we could gather some data. Okay. Let's gather some data. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So multiplying by 1 is easy. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2 times 2, 4. 2 times 3, 6, 2 times 4. 1 o'clock is 7 hours. 1. Uh, 2 times 5. 10, so it's going to be the same as 3. And 2 times 6 is 12, it's the same as 5. So going down, it would be 2 would be 6, 1, 3, 5. Okay. 3 times 3. 2. 3 times 4. That's 12. That's the same as 5. 3 times 5 is 15, which is 1. And then 3 times 6 is 18, which is the same as 4. 4 times 4 is 16, which is the same as 2. 4 times 5 is 20, which is the same as 6. And then 4 times 6 is 24, which is 3. 5 times 5 is 25, which is the same as 4. And then 5 times 6 is 30, which is the same as 2. And 6 times 6 is 36, which is the same as 1. So the first thing we see is it's closed. It's associative. It has an identity. Does it have an inverse? All we have to do to check to see that it has an inverse is there a 1 in every row? Yeah, has an inverse. So this would be a group. This is our second example of a clock with a prime number of hours. We did 5 earlier. We now have 5 and 7. We now have 2 data points. This is beginning to look like maybe this will be the case. Now, there's something really interesting. Let's look at powers of 2. So let's look at the cyclic group generated by 2. It's going to go 1, 2. 2 squared is 4. What's 2 cubed? 8, which is the same as 1, because we're on it, and then it's just going to repeat. So it would actually just stop at 4. So if I look at the cyclic group generated by 2, I only get 3 elements, as the order of 2 equals 3. If I tried the element 4, what would the order of the element 4 be? 1, 4. What's 4 squared? Four squared is 16. We're doing things on a clock with 7. So what would be 16 mod 7? It would be 2. And now what's 2 times 4? 1. So we would get back. So again, this also has as the order of 4 equals 3. You could look at the subgroup generated by 6. What's 6 squared? Which is 1. As the order of 6 equals 2. We could look at what's generated by 3. You get 1, 3, 9 is the same as 2. I could do 3 cubed, or I could just do 3 times 2, right? 3 times the previous, which is 6. I could do 3 to the 4th, or I could just do 3 times 6, which is 18, which is 4. 4 times 3 is 12, which is the same as 5. And 5 times 3 is 15, which is just 1. As the order of 3 equals 6. And if I look at powers of 5, I have 1, 5. 5 squared is 25, which is the same as 4. 4 times 5 is 20, which is the same as 6. 6 times 5 is 30, which is the same as 2. 2 times 5 is 10, which is the same as 3. 3 times 5 is 15 is 1. As the order of 5 equals 6. So what's interesting here is not only is this a group, it turns out this is a cyclic group. This is a cyclic group. Can you give me a number whose powers generate this group? Generated by powers of what number? So is there any number whose powers give you the numbers 1, 2, 3, 4, 5, 6 in some order?
In that order or in
Any order.
three?
3. Anything else? So generator is not unique. So we've just proven a theorem. If you have a cyclic group, it does not necessarily have a unique generator. Let's go back and look at we would gather data. We looked at clock multiplication under 5. Do you think that there's an element whose powers generate this group? What should we try first? What do you think we should try first? And we're trying to find, is there some element whose powers generate the group? 2. Can't try 1 because all the powers of 1 are 1. So let's try 2. Is this cyclic? So if we look at, we start off with 1, 2. 2 times 2 is 4. Right? 4 times 2 is 8, which is the same as,
Oh, under one,
well, it's mod 5. So what is 8 mod 5?
3.
3. And 3 times 2 is 6, which is 1. Let's look at the powers of 3. 3 times 3 is 9. What's 9 mod 5? 4. 4 times 3 is 12. Mod 5 is 2. 2 times 3 is 6, which is 1. And last and least, let's look at 4. 4 times 4 is 16. What's 16 the same as?
1.
1. Okay. Well, 4 is really the same as -1. I don't expect 1 to be a generator. I don't expect -1 to be a generator. Every other number is going to work. So is the cyclic? Yes. 2 or 3 can be a generator. So now we have an interesting observation. When we took p equals 5, we got a group. It was cyclic, and it had generators. When we took p equals 7, we got a group. It was cyclic, and again, we had 2 generators, but this time it wasn't 2 and 3. This time it was 3 and 5. So we've just proven the following theorem. No matter what prime you take, you get a group. It's cyclic. There are exactly 2 generators, and one of them is 3. Does anybody believe all of those? All 4 of them. If you take any prime, it's a group. It's cyclic. It always has exactly 2 generators, and one of those generators is 3. Okay, so probably all 4 of those are not true. Some of them are true, though. How could you try to figure out which ones might be true? What could you do? What should we look at next? We've done 5, we've done 7. What should we study next? 11. And after 11, 15. Or maybe just choose something large. And again, you should really learn how to do coding like this. If you know how to use programming languages, that's great. Microsoft Excel or Google Sheets would be fine for something like this. You could set this up with a cell structure and do clock arithmetic and make these multiplication tables. So I strongly urge you, I'm not giving you large amounts of homework. If you want to make sure you understand the material, the best thing to do is to do problems. If I give it to you as an assigned homework problem, everybody has to do it. And so if you understand things clearly and you're comfortable with it, I'm giving you boring stuff to do. If you are struggling, if you're not sure about this, if you want to really check to see if you understand it, then you can do it, talk to me, talk to your classmates. So I strongly urge you to try to do 11, 13, something like that. Try to write some code, use a Google Sheet, use an Excel workbook. If you're really old, VisiCalc Basic. I've seen some old computers in this building, so I wouldn't be surprised if you could find some old spreadsheet software like that lurking somewhere. But gather data. Most of you, I had breakfast with a former student of mine yesterday, and he admitted to me that something I told him was correct. He's really not using anything he's ever learned from any class with me. Now, admittedly, he's gone into poli-sci and he took a math class with me. You're not going to use most of the facts you learn in most of your classes. You're not going to use the facts you don't learn. What you're going to learn is valuable is the way to attack problems, the thought process. How do I try to use the givens? How do I try to find a way to attack things? That's what I want you to get out of this class. You're going to forget most of the stuff. And when you need it, you can look it up. It's the 21st century. Did I share the story about the table of integrals from my college days? One of my physics professors said you need to have 2 tables of integrals, a big monster that you keep in your dorm room, and a small portable one that you have on you at all times. Nobody does this anymore. Did any of you learn how to use tables of integrals? No, right? It's completely changed. So because facts are so easily accessible, it's great if you know them, it's great if you remember them, but that's not as important. What's really important is the thought process. How do you attack things like this? What we're trying to do now is we've got some groups, we've got some basic properties of groups. You could ask, what kind of structures are possible for groups? Maybe every group is cyclic. Maybe every group has a generator. Well, we actually have a counterexample to that. We looked at 1, 5, 7, 11 under clock arithmetic with 12 hours. Is this group cyclic? Is there some number whose powers generate this group? What's 1 squared? 1. Okay, can't be cyclic. What's 5 squared? 1. What's 7 squared? 1. What's 11 squared? Not cyclic. So we've just proven not every group is cyclic. We've proven not every group is generated by just 1 element. So then the question is this group maybe somehow generated by 2 elements? How can I try to break down this complicated group maybe into simpler groups? And Silverman has a nice passage about something like that. You take something complicated, you break it up into smaller pieces that you can understand, and then somehow you recombine them at the end of the day. And so we're getting a lot from these examples. We saw a couple of examples of groups that, hey, these groups are all turning out to be cyclic, and they're all generated, but not every group is going to have this property. We saw that if n is composite, then it's not going to be a group. And so we have 2 possibilities. One is to be exclusive and just throw away all the numbers that share a factor with n, because none of those numbers are going to be invertible. So we showed if n equals n1 and n2, then the number is not invertible. So no matter what number you give me, if it has a common factor with n, it can't be invertible. So I'm down to just looking at the numbers that are relatively prime. Can we show that that forms a group? The other possibility was to say, well, let's just look at n is prime, because then if n is prime, everything from 1 to n minus 1 is relatively prime to n. And we usually write p to just highlight the fact that it's a prime so that when you glance down, you know, okay, I'm talking about a prime, talking about a prime, talking about a prime. Okay, so the question is, if p is prime, is the set 1, 2, dot, 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 p minus 1 a group on clock multiplication? So we have to check several properties. What's the easiest property to check? What's going to be the easiest property to check? You've got
Associativity?
associativity. There's a couple that are, yes, it inherits it. Inherits from regular multiplication. All right, we got 25% of the way there. Not bad. Can somebody get us to 50%? What's the next one to check? There's only 3 properties left. What's another thing? What do you think is going to be easy to check to show? Identity. Do we have an identity? Yes, what is it? 1. Again, it inherits. We'll say just 1. All right, so now we're down with the harder ones to check. Are there inverses? And is it closed? So let's look at closure. Assume m and n are in the set 1, 2, dot, 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 p minus 1. And m times n is not in the set when we look at it mod p. So what's the only possible value if m times n is not in the set? Get m times n mod p. If I give you a clock with 13 hours, what are the only possible values when I look at a number mod 13? What are the possible values if I look at a number mod 13? 0 to 12. So if it's not closed, and it can't be from 1 to p minus 1, what's the only thing that it could be? What's the only thing that's left? What does it have to be if it's not going to be closed? 0. M times n mod p has to be 0 if not closed. So we have m and n in the set 1 to p minus 1 with m times n equal to 0 mod p. What does it mean to equal to 0 mod p? If 2 numbers are the same on a clock, what does it mean? So if I tell you 2 numbers are equal on a clock, what must be true about their difference? Not equal to 0. If I have a clock with p hours and 2 numbers are the same mod p, what must be true about their difference? It could be 0. It's a multiple of p. So there exists a b such that m times n equals 0 plus some multiple of p. So m times n is b times p. How can we get a contradiction from this? So m and n live between 1 and p minus 1, and their product is a multiple of p. So we need to use a small fact from number theory. If a prime divides a product, it divides at least one factor. Okay. So if I tell you 7 divides x times y, 7 divides x, 7 divides y, or 7 divides both. This comes from the unique factorization. I write x as a product of primes, I write y as a product of primes, and then if neither x nor y is a multiple of p, how can p be dividing themselves? You would have two different factorizations. Are people comfortable just assuming this fact? So if b does not equal 0, then p divides m or p divides n, contradiction. And we know m times n is not 0. So the only possibility left is b equals 0 and m times n is 0. So b equals 0 and m times n equals 0. That's impossible, as each is greater than or equal to 1. So we do have closure. If I take two numbers and I multiply them, I've got to get another number between 1 and p minus 1. The only other possibility would be I could have gotten 0, but if I get 0, then that means m times n is a multiple of p. And if it's a multiple of p, either p divides m or p divides n. And I can't have that because m and n live between 1 and p minus 1. So if they live between 1 and p minus 1, how could they be a multiple of p? This beautiful result in red is this composites. Actually, I'm going to use the darker green. If a composite divides a product, must it divide at least one factor? What do you think? We know if a prime divides a product, it has to divide at least one factor. Is that going to be the case for a composite? So give me, you're now on the hot seat. You've got to give me a composite, and you have to give me a product that it divides, and it doesn't divide either term. What's your composite? Well, somebody can help him. I need a composite that divides a product, but doesn't divide either term. Somebody give me a composite number. 6. Can you give me a product that 6 divides? Okay, but you have to write 12 as a product.
Oh, 4 times 3.
4 times 3. So 6 divides 4 times 3, but 6 doesn't divide either. I would have done 6 divides 2 times 3. 4 times 3 is perfectly good, right? This is something special about primes. So whenever you get a result, you try to see how far can we push it. So have we shown that this is going to be a group? Have we shown all 4 properties? What have we not shown? Inverse. So what we have to do left is inverses. So inverses. If m is in 1, 2, ... p minus 1 with p prime, then there is an n in this set with m times n congruent to 1 mod p. So this needs to be shown. If I give you a specific p, you can roll up your sleeves and you can do the calculation. To prove this in general is going to require some work. So it uses one of my favorite results in all of mathematics, the Euclidean algorithm. How many of you have heard of the Euclidean algorithm? So the Euclidean algorithm helps you find the GCD of two numbers efficiently. There are a lot of things in mathematics that are trivial to write an algorithm that will do it, but the universe will die a heat death many times over before it's done. Is it hard to factor a number? If I give you a number, can you factor it? With unlimited patience. How would you factor it? Test every number, right? Factorization is easy. You know, I don't understand all these movies about people coming up with these secret ways to factor numbers quickly for encryption. It's trivial. Well, so factor by trying all numbers. If x equals 10 to the 400, right, that's going to take way longer than we have. So I'm setting us up for a Tuesday lecture, which is going to be more applied because we've been doing theory for a while. So we're going to return to some of the stuff we need for cryptography, which is going to be proving the stuff for these clock groups. We can't do something of size 10 to the 400. Your algorithm can be improved. If x is composite, then I can write x as maybe a, b, and at least 1 is less than or equal to the square root of x. Because if I can write my number as a product, both numbers can't be greater than the square root of x, or their product would be greater than x. So instead of having to check all the numbers up to 10 to the 400, if the number is composite, how high do I have to check? Which is 10 to the 200, right? Did I do the joke about the sun going nova in 5 billion years?
Yes.
Yes, I just used this in a research class I was doing. Oh my God, you know, it really doesn't matter if the sun goes nova in 5 billion or 5 million years for us, right? Going from 10 to the 400 to 10 to the 200, that's a tremendous improvement, and you're still screwed. I would use stronger language, but this is being recorded and posted, and I don't want to violate the YouTube permissions, right? 10 to the 200 is still beyond anything we can do. We need to find a way to do this efficiently. Nobody has publicly given a way to factor efficiently. I will stay around today. Anybody has any questions, happy to chat.